Good afternoon, students. Welcome to the lecture of Operation Research. In the last lecture, we have started studying how to find out the primal dual problem of a given primal. We have studied some rules also of finding a dual from its primal. Some rules states that first we have to convert. Let us just recall rules. First, we will convert the objective function to maxima if not. If the constraints are of greater equal sign, then we will convert it to less equal sign. Okay. If an equality constraint we have, we can replace it with the two inequalities going in opposite directions, and then second inequality, which is with greater equal sign, can be further changed to less equal by multiplying with minus 1. Then every unrestricted variable is replaced by the difference of two non-negative variables. Then step number 5 tells us the standard primal form. Okay, there are two standard primal forms actually. First is all constraints are of less equal sign, objective function is maxima. Second standard is all constraints are greater equal sign, objective function is minimum. If you observe, if I start with this first form as a standard form, standard primal form, then its dual will have this kind of structure. That is object constraint will of greater equal sign and objective function is minimum. Because this is actually a primal dual relationship. Okay, and while solving the examples, we will take care or we will start with the first standard primal form. That is all constraints are less equal type and objective function is a maximum. Once we find this standard primal form, then the dual can be obtained very easily by transposing the coefficient matrix, by interchanging the right hand side constant with the coefficients of objective function, changing the inequalities from less equal to greater equal, and minimizing the objective. Okay, then we have seen some of the examples also. While solving the examples in detail, I told you how to find out the duals also. Later, we have started the important theorem, and the first theorem we have proved is the dual of a given primal is the prime. That is, if we find twice the dual of a given LPP, then it gives you the original. Okay, and this is what the proof we have started with. We have written a standard primal form. We have found its dual. Then to find one more dual, we have converted this dual into a standard primal form. After converting this to a standard primal form, again we have found its dual, and then that dual we have written by observing the negative and all. We have written this in this form, which is exactly identical with the original LPP. The alternative proof we have given or we have studied by using this summation notation. Whichever you feel easy to write, you can start with. Okay. Now in today's lecture, we will go for next important theorems. One statement we have discussed already while solving the example. Okay, what is that statement we have studied? Suppose if second constraint of an primal is an equality, then the second dual variable is unrestricted inside. This we have studied, no? Similarly, the second one we have studied is suppose if the third uh, variable is unrestricted in sign of the primal, then third constraint we will get it as an equality. Therefore, we will prove both the results and then we will go further. Okay. So for this theorem number 2, I will write as if the if the kth constraint of the primal kth constraint of the primal is an equality then it's not it's then the dual then the dual variable wk is unrestricted in sign. While solving the example, we have seen this, we have observed this, but now we have to give the textbook proof of this statement. Okay, what is given to us? Take the constraint of the primal is an equality. Therefore, we will write one LPP where the kth constraint is equality, and then we will try to write its find its dual, right? Consider the LPP with take the constraint as an equality. kth constraint as an equality. Okay. Therefore, here you will write that LPP maxima is z is equal to C1x1 plus C2x2 plus Cn xn subject to the constraint. What is the first constraint? A11x1, A12x2, so on up to A1n xn less than or equals to B1. Say I will not write second and third. I will write directly the kth one. What are the coefficients in the kth one? Is it AK1? Less than or equals to B, right? We write its nth constraint as well. What is the mth constraint? AM1 x1, AM2 x2, so on up to sorry. Kth constant I should assume as an equality. No, but here I have to write equality. And this last one is less than or equals to Dn, and all the variables x1, x2 up to xn all are non-negative. Okay. Now just tell me whether this given LPP is in a standard primal form.
No, ma'am.
No,
No.
ma'am.
Objective function maxima, all the constraints should be less equal, but here the kth constraint is not less equal. Then how can we replace this kth constraint, equality constraint, by two inequalities? Okay, two inequalities going in opposite direction means one inequality is with less equal, another is greater equal. Later we will convert that greater equal inequality to less equal inequality, right? Multiplying with minus. Okay. Now what should I write here then? Replace eighth equality constraint by two inequalities. Okay, what are the two inequalities? AK1 x1, AK2 x2 plus AKN xn. First I will write less than or equals to BK. Next AK1 x1, AK2 x2 plus AKN xn greater equal by BK. Okay. Now again we will convert them both of them to be less equal. The second we will replace again by AK1 x1, AK2 x2 plus AKN xn. This is the first one, less than or equals to BK. I'll keep as it is. The second one we will start multiplying with negative. Minus AK1 x1 minus AK2 x2 so on. Sorry, minus here. Minus AKN xn less than or equals to minus BK. Now what we will do? We will replace this kth constant by two inequalities in statement number 1. Okay. The above system of equation 1 becomes. Okay, what is the system of equation? Maximize z is equal to C1 x1, C2 x2 plus Cn xn subject to the constraint A11 x1, A12 x2, A1n xn less than or equals to B1. Continue AK1 x1, AK2 x2, AKN xn less than or equals to BK. What is the second one? Minus AK1 x1 minus AK2 x2 minus minus AKN xn less than or equals to minus BK. And what should be my last? am1 x1 am2 x2 plus amn xn less than or equals to bm x1 x2 2 xn all are non-negative. Okay, now this whatever the system we have written is in the standard primal form. Now what we will do, we will try to write its dual. Okay, while writing the dual, how many variables are needed now? Dual variables. Yes, anyone can students, how many dual variables are necessary?
Say m plus 1.
Yes, it's m plus 1 because original number of constraints are m, but we have split out that kth one into two parts. Okay, therefore here what I will do, for the first constraint let us write the variable w1. For the second let us write, sorry, this is not second, this is kth. Now for kth what I will write, first part of kth constant is wk dash variable I will use. Second part of this kth constant I will use the dual variable wk double dash, and for the last one I will use the variable wm. Is it fine? Now I will try
Yes,
to
ma'am.
write its dual. Now while writing the dual, what will be the objective function?
Minimize z is equal to b1 w1 and so on.
Yes, minimize z w b1 w1 b2 w2 till bk we have to go now. bk wk dash minus bk wk double dash. Correct, no? bk
Yes, ma'am.
wk dash minus bk wk double dash. Okay. And continue this up to bm w. Subject the constraints. Now this first column we have to write as first row. 1, 1, 1, 2 till k1 plus ak1 minus ak1 up to a m1. Okay. Now while writing this coefficient of these two, what we will do, we will take the variables common and we will, sorry, we will take the coefficient common and we will write the variables together. Okay. Let me show you how. First is 1, 1, 2, 1, k1 m1, right? Now a11 w1 a21 w2 for ak1 is wk dash minus ak1 wk double dash. Correct now? This sort of statement it will be ak1 wk dash minus ak1 wk double dash. Now what I am going to do, I am going to take ak1 common from the two. Correct? And what I will write? I will write remaining terms in a bracket. Ak1 I am taking common. Wk dash minus wk double dash I will put it in a bracket. And last it is am1 w1 wm. What it is? Greater equal by? Hmm. What should be my right hand side constant in the dual?
C1.
Yes, it is C1. Okay, let me write the second one. What is my second constraint? A12 W2, sorry, A12 W1, A22 W2, so on AK2 WK dash minus WK double dash and continue AM2 WM greater equal by C2. Let us check. Correct na? 1, 2, 2, 2. K2 we will take common. WK dash minus WK dash double dash AM to WM. Okay. Let me write last one. A1N W1 A2N W2 so on AAN WK dash minus WK double dash plus AMN Wm greater equal by Cn. Correct, no? And all the variables W1, W2, W3, Wk dash, Wk double dash till Wm all are non-null. Correct? Okay. The same kind of change we can observe in the objective function as well. Here also one can take bk common and we remain with wk dash minus wk double dash. Now what we will do? We will replace this difference wk dash minus wk double dash by wk only. Therefore, what here I will do? Replace wk by wk dash minus wk double dash. Correct? Then what is the nature of wk? Here both the variables are non-negative. Both these wk dash and wk double dash are non-negative, and this wk we are writing as a difference of two non-negatives. Therefore, the value of wk depends upon the relation between the two values. Correct? That is, if wk dash is greater by wk double dash, this is non-negative. If not, it will be non-positive. Therefore, the value totally depends upon the relation between the two. Therefore, here this wk becomes unrestricted.
Yes, ma'am.
Hmm. Correct? Therefore, what will be my effect on the dual? Maximize ZW is equals to B1 W1, B2 W2, so on, BK WK till BM WM subject to all those constraints.
Ma'am, it's minimize Z.
Oh, sorry. Please, please. What I have written here about AK1 WK so on AM1 Wm greater equal by C1. And let me write the last everything. And what about the variables? W1, W2 till Wk minus 1 and Wk plus 1 to Wm all are non-negative and Wk is unrestricted. What we have observed, if the kth constraint of the primal is an equality, then this kth dual variable is unrestricted in set. Okay, hence the proof. Or you can rewrite the statement of the theorem. Right? Understood? How the proof is easy? Let me go for the next
Yes,
theorem.
ma'am.
Theorem number 3. What the theorem says now in the reversion. If the pth variable of the constraint is unrestricted, then the pth constant is equal. If pth variable of the primal is unrestricted, in sign, then pth constraint of the dual is an equality. How should we start the proof of this theorem?
Yes, ma'am.
How should we start? How should I write the proof?
And we'll consider a primal, and
Hmm?
in that we'll show one variable to be unrestricted, which is the difference of two,
Hmm.
variables.
Hmm. And we will just find its dual and we will observe the
Yes, ma'am.
constant nature, right? Okay, here we will start with, I think it is better to go on the next page. Maximize z is equal to, say c1x1, zx I should write, c1 is to suppose cpxp somewhere, pth variable we are considering, na? Up to cn xn subject to constraints 11x1, 12x2, 1p xp, 1n xn less than or equals to b1. Let me write one more, a21xn, a22x2 plus a2pxp, so on, a2n xn less than or equals to b. Right? Let me write somewhere last, am1x1, am2x2, ampxp, so on, amn xn less than or equals to bn, and what about the variables x1, x2 to xp minus 1, and then xp plus 1 to xn, all are non-negative, and xp is unrestricted. xp is unrestricted or unrestricted in sign. Now whether this primal whatever we have written is the standard primal form?
No, ma'am.
No, it's not, because we don't have all the variables to be non-negative. This one variable is unrestricted. Now what we will do? We will replace this unrestricted variable with the difference of two non-negative. Okay. What I will do? Let us express xp as difference of two non-negative variables. Difference of two non-negative variables. Say xp dash and xp double dash. That is, now let me put the value of xp as xp dash minus xp double dash. Okay, now to the above LPP becomes. Okay, now what we will do is to substitute correspondingly the change of the variable xp. Therefore, this is maximize zx equal to c1x1, c2x2. Somewhere here in between cp xp we have written, na? That is cp xp dash minus xp double dash till cn x. Let us do the corresponding changes in the constant as well. Subject a11 x1, a12 x2. Somewhere in between we have written a1p xp, that is xp dash minus xp double dash, continue a1n xn less than or equals to b1. Let me write one more, a21 x1, a22 x2, a2p xp dash minus xp double dash in a2n xn less than or equals to b2. Let me write the last one, am1 x1, am2 x2, so on, amp xp dash minus xp double dash till amn xn less than or equals to bm. And now what about the variables x1, x2 to xp minus 1, xp dash, xp double dash, xp plus 1 till xn all are nano. So what we have done while converting this to a standard primal form, we have increased the number of variables by 1. Right? No? Initially the number of variables were n. Now we have made them as n plus 1. Okay. Then what about the number of variables and number of constraint in its dual? Yes. What is the number of constraints and number of variables in the dual problem? Can anyone tell me?
Number of constraints will increase by one.
N
And
plus 1, sure. Hmm.
yes,
And what about number of variables? Number of dual variables.
it will be m.
Yes. Okay, I think I have already explained this that the number of variables and number of constraint, the role will get exchanged in its dual. Correct, no?
Yes, ma'am.
Just find the dual of above LPD. Okay, now what are the number of which are the number of variables we were using? Suppose for the first constant I am using W1, this is W2, and let it be Wm. Right? Now you will write the constant. Now while writing the constraints, here when we reach to this part now, here also we have to write two different constraints. One constraint is collecting the coefficients of xp dash, another constraint is collecting the coefficients of xp double dash. But if we observe, the coefficients of xp and xp dash and xp double dash are same. Only the change will be in the sign, negative sign. Correct now? Because the coefficient of xp dash is a1p, coefficient of xp double dash is minus a1p. If all the coefficients are same in both the constraint, only the change will be there in the sign. Okay. Therefore, what will be my LPP dual? This is minimize ZW B1 W1 B2 W2 so on Vm Wm subject to the constraint. Now we are going to write first column as first row. This is A11 X1 21 sorry not X1 W1 I should write no? 1121 and M1. These are the coefficients I given. 11 W1 21 W2 so on up to M1 W M greater equal by what?
C1.
Yes, good. First constant I have written. Let me write second also. 12 W2 22 W2 12 1222 M2 correct. 1222 M2 WM greater equal by C2. Now write the pth constant P and this coefficient. What are the coefficients? 1p, 2p, mp. A1p, W1, A2p, W2, so on. AMP, WM greater equal by what is the coefficient? Corresponding coefficient. Sorry, I have to put dotted lines here. Yeah. Each one I am writing. No? A1p, W1, A2p, W2, so on. AMP, WM. What is the corresponding coefficient?
It is plus CP.
It's plus CP. Good. This is plus CP. Now this second one we will write what are the coefficient? Minus A1p, minus A2p, minus AMP greater equal by minus CP. greater or equal by minus Cp. And what will be the last one? A1NW1, A2NW2, ANNWN greater or equal by C. Right? Now observe these two pair of inequalities. If I observe the pair of inequalities, these two are exactly same. Okay. If I multiply the second inequality by the negative sign, what will happen? This negative will get absorbed and same inequality we will obtain with less equal. The one inequality is in greater equal sign, another one equality is in less equal sign. Therefore, we can write combining these two as an equality. Okay. Combining the two inequalities combining the two inequalities. Shall I name as P and P plus 1? We get, or we get it as an equality. We get it as an equality. What is the equality? A1P W1, A2P W2, so on. AMP WM is greater equal, sorry, is equal to C2. Correct? Therefore, we have started with pth variable as unrestricted, and here which constant we have obtained as an equality? Pth constant we have obtained as an equality. Okay, here you can write this as pth variable is unrestricted. We have obtained pth constant as equality. Yes, any doubt on the proof?
No,
No,
ma'am.
ma'am.
The proof we were writing actually very similar to the example. How we are solving the example, we were writing the proof in the similar fashion. Okay. Now we will just move towards next theorem, which tells us the relation between the solutions of primal and dual problem. Because the theory arose in that sense actually, in order to find out the solution between the primal and dual, right? Therefore, now we will go towards the next theorem, which gives us the relation between the feasible solutions of primal dual problem. What is the relation between those solutions, right? Let me write this as my next theorem number 4, I think. If x is if x is any feasible solution, x is any feasible solution to the primal, or to the primal problem, and capital W is any feasible solution to the dual problem, then prove that Ex is less than or equals to B transpose W, that is Zx is less than or equals to Zw. This is what the relation between the feasible solutions of primal and dual problem. Let us try to understand. X is feasible. It is said feasible, not optimal. Right? Among all feasible, you have to find out basic feasible. Among all basic feasible, whichever gives us the optimum value of objective function will be my optimal feasible solution. But here x is given only feasible, right? Feasible solution. W is feasible solution to the dual. Then we want to prove that Cx is less than or equals to B transpose W. That is Zx is less than or equals to Zw. Value of objective function in the primal is less than or equals to value of objective function in the dual. This is what we want to prove. Now here we will start with the two solutions. Now x is assumed to be the number of variables. Now vector giving number of variables in the primal, and generally we write n number of variables. W is a feasible solution to the dual. How many variables we were writing in the dual? M variables we were writing. Okay. So let me write. Let capital X is equal to x1, x2 to xn, and capital W is equals to W1, W2 to Wm be any feasible solution, any feasible solution to the primal and dual problem respectively. Primal and dual problem respectively. Our aim is to show Cx is less than or equals to B transpose W. Okay, I think everyone is familiar with what is Cx, what is B transpose W, what are the constants. Or if you want, I can write primal LPP and dual LPP as well in a summation form. Yes, maximal Z is summation Cj Xj, correct now? J equal to 1 to n subject to the constraint. Yes. Summation Aij xj j running from 1 to n less than or equals to I equals to 1 to m. Correct now? I'll
Yes,
put it
ma'am.
in summation form. Now I will write its dual LPP. What is a dual LPP? Minimize Zxi, right? Here I will write Zw is equal to summation I running from 1 to n subject to the constraints. Yes, summation I running from 1 to m and is greater equal by Cj. Right? And this is true for all
मॅम
j.
समेशन इथे पण एम येईल ना.
What?
मिनिमाइज ZW इक्वल टू समेशन I from 1 to m
Oh,
येईल.
sorry. Here it is also m. Good. Dual variables are m in number. Correct. Therefore, it is m. Okay. This is the primary dual LPP we have written. Now we will start with this left hand side Cx, and we will prove that this is less equal by B transpose W. The proof is very easy in 2-3 steps only. Therefore, let me start with considering Cx. Okay. What is Cx? Summation j equal to 1 to n Cj xj. Correct now? Cj xj. Now I will replace this Cj by knowing this constraint, or I'll give the numbering to every constraint. 1, 2, 3, and 4. This will be better. Now what I'm going to do? I'm going to replace the value of Cj by this equation number 4. What Cj will be? Cj is less equal by this summation. Correct now? Cj is less equal. This summation j equals to 1 to n as it is. Now we are replacing this Cj, which is less equal by summation I equals to 1 to m aij wi into xj. Right? Reason from 4. Clear? Now I'll just rearrange the terms of a summation, and I'll take this first sum, I sum first, that is I equals to 1 to m. I'll rearrange the terms j equals to 1 to n, aij xj, and then I'll take w1. I just rearranged the terms, right? Now summation aij xj, this is a constant of our primal. Therefore, by 2, summation j aij xj is less equal by bi, no? Let me put it. This middle term is less than or equals to bi. Therefore, this is less equal by summation I equals to 1 to m as it is. This term we were replacing by bi, and this becomes summation bi wi. And in summation bi wi is nothing but, in a matrix form, this is b transpose w. And hence the proof. Yes, any doubt?
Ma'am, please repeat.
Let me repeat. we have written the primal and dual LPP in the summation form. Okay, if a primal objective function is summation Cjxj, whenever j is there, it will run from 1 to n. Whenever I is there, a parameter, it will run from 1 to m. Therefore, this constant equation, so we will write summation j equals to 1 to n aijxj less than or equals to bi. And how many such are there? I 1 to n. Therefore, there are in all m constant. Correct now? B1, B2 to Bm. M constant will be there. Now, if I want to find its dual, we know the objective function is BI, no doubt I is running from 1 to M. And the constraints are we are going to just transpose, no? Means we are going to change the summation point of view. Aij, Wi, but now the summation I is running over M. Here it is running over J. And this is greater than equal by Cj. In order to prove the result, we will start with Cx. What is Cx? Cx is a matrix form actually, which is equal to summation Cjxj. Now what we were going to do? We were going to use this fourth equation, Cj. We will put the value Cj less equal by summation Aij, This is what I have done. I have just substituted. Then we have just interchanged the positions of the summations. We have written this summation I first, summation j later, okay, and then aijxj together, wi I have written separately. But this aijxj, summation aijxj is less than or equals to bi, no? From 2. Correct, no? Summation bi, that now if I replace this bracket by bi less than or equals to bi, it becomes summation bi. But summation bi is nothing but the objective function of the dual. Therefore, this is in a matrix form we can write as B transpose W. Hence, we have proved Cx is less than or equals to B transpose W. That is, Zx is less than or equals to Zw. It is objective function of the primal is less than or equals to objective function of the dual, but for the feasible solution. This we are not writing for the optimal solutions. Okay. Next theorem we will see in case of the optimal solutions as well. Let me write this as the next theorem number 5. If x cap is feasible solution to the primal, means actually this theorem giving us the condition when this feasible becomes optimal, and W cap is feasible solution to the dual such that, what such that Cx cap is equal to B transpose W cap. Cx cap is equal to B transpose W cap. Then prove that X cap is optimal solution. X cap is optimal solution to the primal, and W cap is an optimal solution to dual. Okay, try to understand. Previous theorem tells us that for any feasible solution, this relation holds. Zx is less than or equals to Zw. That is, value of objective function of the primal is less than or equals to value of objective function in its dual. But if we just add this condition, knowing x cap is feasible solution to the primal, w cap is feasible solution to the dual. That is, among all feasible solution, x cap is one of the feasible solution and w cap is also one of the solutions, such that this condition holds. So this condition is important. C x cap is less than or equals to B transpose W cap. What this gives us? It gives us that value of objective function for both the feasible solution, for both the problems is same. Correct now? Then our aim is to prove that X cap is optimal solution for primal and W cap is optimal solution to the dual. W cap is optimal solution to the dual. Okay, let me write just let X cap is feasible solution to dual, or sorry, to primal, and W cap is feasible solution to dual such that, what such that, Cx cap is equals to B transpose W cap. Okay, but what we have proved in the previous theorem, hmm? What we have proved for in the
Cx
previous
cap is
theorem?
less than equal to
Yes,
B
if
transpose W cap.
x, yes, I write just one statement. If x is feasible solution to the primal and W is feasible solution to the dual, then Px is less than or equals to B transpose W cap. Oh, sorry, B transpose W. Simply, na? Px is less than or equals to B transpose. Let me call it as statement 1 and statement 2. Now, what the job I will do, I will just substitute the value. Uh, Instead of x as a feasible solution, I will take x cap as a feasible solution to the primal. This statement is true for all the feasible solutions, no? Of the
Yes, ma'am.
primal. Therefore, instead of x, I will take x cap as the feasible solution. Then what will happen? Sorry, instead of w, I will take the feasible solution as w cap. Let w cap be feasible solution to dual, and x is feasible solution to the primal. Now what will happen? I'll just change. Okay. Now what will be the statement number 2? Is it Cx less than or equals to B transpose W cap?
Yes, ma'am.
Okay. Now what I will do? I will just replace this B transpose W cap at Cx cap from 1. This is from 1. Is that clear? From 1, I am just replacing B transpose WK. So what we have obtained, the value of objective function at x cap is greater equal by the value of objective function at any feasible solution x. Therefore, may I claim x cap is an optimal solution to the primal?
Yes, ma'am.
Correct, na? Try to get me. X cap is the value at x cap, the value of objective function of the primal is greater equal by the value of objective function at any feasible solution. That's why x cap gives me the optimal among all feasible solutions. Therefore, this implies x cap is optimal solution to the primal. Okay. Similarly, what we will do? Similarly, here we have started with W cap is feasible solution to the dual and X is a feasible solution to primal. Now what I will do? I will do reverse. I will start with X cap is a feasible solution to the primal. X cap is feasible solution of primal and W be any feasible solution to the dual. Okay. And again by the previous theorem what we were writing? Cx is less than or equals to B transpose W. Na? For what can I write here? C x cap less than or equals to B transpose W. Correct, no? By statement, what is the number I have given? 2. Is it fine?
Yes,
Yes,
ma'am.
ma'am.
Now we will replace Cx cap is equal to B transpose W cap. Correct, no? This is statement number by 1. I have put this equality. Cx cap is equal to B transpose W cap. Now look at this. The value of dual, the value of objective function of the dual at W cap is less than by any value of objective function at any feasible solution W. See, whenever we are seeing dual, the objective function is minima time. Therefore, here this W cap is giving us the minimum objective function than any other feasible solution W. Therefore, may I say W cap is an optimal solution to the dual?
Yes, ma'am.
Yes, ma'am.
Correct now? Because this objective function is minima type. Therefore, W cap is optimal solution to dual. Here I'll write for minima problem. Because whenever we are taking the primal to be maxima, the dual should be minima. Therefore, here W cap is giving us the minimum value of objective function than any other feasible solution W. Therefore, W cap is giving us an optimal solution to the dual in case of minima problem. Hence, what we have proved, X cap is optimal solution to the primal, W cap is optimal solution to the dual. Therefore, if we have two feasible solutions to the primal and dual problem respectively, where the value of objective function is same, value of objective function of primal and value of objective function of the dual is the same at the two feasible solutions, then both these solutions, feasible solutions, are nothing but the optimal solutions. Both these feasible solutions are nothing but the optimal solutions. If you still have a doubt on this today's lecture, you can ask. Otherwise, in the next lecture, we are going to study basic duality theorem. In that basic duality theorem, we were going to understand the conditions. When the primal has optimal, what is the nature of solution of the dual? If it is finite optimal, what is the nature of the solution of the dual, and vice versa as well. That we will study in the next lecture. But whether if you have any doubt on this today's lecture, you can ask. Therefore, this condition is essential for feasible solution to become optimal solution. Value of objective function should be same. Yes?
Yes,
If
ma'am.
you have any queries on this, you can ask. No queries, it
No, ma'am.
seems to be good. We will stop there. Okay? Thank you for being with me for this lecture. Thank you.